Welcome back. We have a new physics problem for our contestant. It is about a conducting bar that slides down two rails with a constant magnetic field running through it. Our 5 questions are shown, so let's get started. Question number A. Determine the current in the circuit when the bar has reached a constant final speed. As you can see, our contestant is using the magnetic flux and the area and the magnetic field, and it looks like x is how far along the bar has slid times the length of the bar to get the area. Substituting what he knows in for the area, he gets the magnetic flux, and now he's using a second equation. It relates the change in the magnetic flux to the voltage running through the bar. Here it is. And we know that the rate at which the bar goes down compared with respect to time is just velocity. And he relates voltage to current, and there is our final answer. So moving on to our second question, determine the constant final speed of the bar. It looks like our contestant's going to use a third equation found on our equation sheet, relating the force, the current, the length of the bar, and the strength of the magnetic field. And it looks like he is drawing out a diagram of the bar rolling down. And he has the three forces that are being... Nope. Looks like our contestant has only two forces. He's missing the normal force, but that is, I guess, irrelevant because there's no friction, of course. And now it looks like he is going to substitute in what he knows for current found in the previous problem. Yes, here we go. And now we have an integral. Yes, but the length of the bar is constant, so it is a fairly simple integral. Looks like it's just going to be L times L, which is L squared. And now we have the force of the magnetic flux going upwards, opposing the force of gravity. Yes. And the terminal velocity occurs when the force of gravity is equal to the force of the magnetic field. And that is because there will be no acceleration, so it will be terminal velocity. And now it looks like our contestant is trying to find the force of gravity that is opposing the force of the magnetic field, and that is mg sine of theta, setting it equal to the force of the magnetic field. And it looks like our contestant will isolate the terminal velocity to get the final answer. Here we go. Our final answer, folks, mg sine of theta times the resistance over the magnetic field squared times length of the bar squared. Moving on to question number 3, determine the rate at which energy is being dissipated in the circuit when the bar has reached its constant final speed. And we know that energy, the rate at which energy dissipates is just power, because that is just change in energy over time. And we also know that power is equal to the current times the voltage. And we know what current is, and we know what voltage is. So it looks like he's going to substitute those in for the power equation. Yeah, here we go from question number 8. And here is the substitution. Oh, looks like our contestant made a little mistake, but no worries, fixed it. And now we have the velocity, the terminal velocity. Looks like he is substituting that in. That's a lot of squares. A lot of squares. And let's just, before we continue, remind ourselves what the terminal velocity was from the previous problem. And it was the resistance times mg sine theta over b squared L squared. And it looks like he simplifies it to just the power is r mg sine theta squared. Moving on to question number D, express the speed of the bar as a function of time t from the time it is released at t equals 0. And we know that the force of the bar, that is the overall force, is just the force of gravity minus the force of the magnetic field, substituting in what he knows. Oh, yes, and also acceleration is just the change in the velocity over the change in time. And it looks like he is substituting what he knows and moving the mass, to the other side. And now it looks like our contestant is doing some calculus, rearranging the problem. And our contestant is substituting constants for other constants to simplify the integral. And I hope you all succeed in calculus class. It looks like he's getting rid of the plus c and just turning it into d. So now we have a unknown constant. It looks like he's going to have to solve for d. Yes, and it looks like to solve for d, he knows that at time equals 0, the velocity is equal to 0, and he's going to plug those two known quantities in to solve for d. And here we go, folks. We now know that when the velocity is equal to 0, d has to be equal to a to make the equation work. So d is just a. And it looks like he is going to simplify it even further by factoring out the a and the c. And then finally substitute in his known quantities of a and c that we substituted out in the first place. And it looks like our final answer, there we go, for question number D. The final question coming up is, suppose that the experiment is performed again, this time with a second identical resistor connecting the rails at the bottom of the incline. Will this affect the final speed attained by the bar, and if so, how? Justify your answer. So it looks like our contestant is drawing out the two magnetic fields, one on the left side, one on the right side, and as the bar slides down, one of them gets stronger, the other one gets weaker, and he has drawn out the magnetic field, the magnetic flux. Sorry, looks like he's using the right-hand rule to figure out if the currents are both facing the same direction, and it looks like they are. And let's see if he goes even further. Since both of the currents are going out of the page, then the current running through the bar is twice as strong as it was before. There was only one connection, or only one resistor at the top of the page. And let's see if he makes the next logical jump. Yes, here we go. Therefore, the terminal velocity will be half of what it was before, because the force that is being produced by the magnetic field is twice as strong due to their current being twice as strong. And we can see this because of the relation between the current and the force. Well, that's all we have for today, folks. Thank you for tuning in to Tim's Physics News. News you can't use.